Hello my dear students, welcome back to Aditya Tutorials. I am Rahul and in this video I continue the Henry's Law students. I think you remember in the previous video I was explained briefly on the Henry's Law. Okay, and today I'm going to solve some problems on the Henry's Law and also we're going to see some basic applications of the Henry's Law. Let's see solve one problem here. Here is a question. The question is find the solubility of nitrogen in liter of water at 293 Kelvin given that partial pressure of nitrogen is 0.987. The unit is bar. The Henry's constant for the nitrogen is 76.48 kilobar. From the Henry's law we know that is a partial pressure of nitrogen is equal to Henry's constant, that is Kh, multiplied by mole fraction of nitrogen. And here the pH is given, that is a Pn2. It is given the Pn2, that is the partial pressure of nitrogen, is given 0.987, and Kh value here we have, that is 76.48 kilobar, means it is 10 to the power of minus 3 or plus 3, it is a plus 3, and here is a bar. Okay. Now come to the part, we have these two terms, but we don't have this term. The mole fraction of nitrogen, N2, in liter of water. And here we have the formula, the number of moles of nitrogen divided by number of moles of nitrogen plus number of moles of water, H2O. Okay, now come to the point. Here, compared to number of moles of water and number of moles of nitrogen, if you compare these two values, here N2, that is number of moles of nitrogen, is neglected as compared to number of moles of H2O, because it's a liter of what we are taking. So therefore mole fraction of N2 is equal to number of moles of nitrogen divided by number of moles of H2O, and that is equal to number of moles of nitrogen we required. So how we get that? So we write only simply here N2 divided by, so here one value I already explained, that the liters, the number of moles of water, that is H2O, given by given weight of the water, that is 1 liter, the 1 liter of water mass is 1 kg, that is 1000 grams, divided by molecular mass of water, it is 18, and that we get here 55.55. This is important value. In one of the video I was told you that this is important value, how to remember it. Okay, that value I'm going to write here, 55.55. Okay students, let's move to the next part. So here whatever the values we have to substitute that. That is partial pressure is 0.987, that is equal to Kh value, that is 76.48 into 10 to the power of 3 into this value, that is a mole fraction, that is number of moles of nitrogen, divided by 55.55. Okay, after that we get here N2, number of moles of N2 is equal to, that is 75 okay, let it be 75.4. instead of that I will use some exact values here, that is 7.169 into 10 to the power of minus 4 moles. 4 moles here. Or else we can change it to millimoles by 0.7169 millimoles. Millimole. So this is the solution for this question, students. Let's see the application of Henry's law. We see some of the applications of the Henry's law. So this is called as a mount climbing. At the high altitude, the concentration of the oxygen is low. Okay, and also the pressure, that the partial pressure of the oxygen is low, because on the Earth's surface you can see that this is the atmosphere. As you go upwards, the partial pressure of particular gas decreases. The partial pressure decreases. Okay. Now what happens when a person is climbing a hill? Here, the oxygen concentration is low and the partial pressure is also low. When the person inhale the oxygen, so he get a less amount of oxygen. That's the first case. The second case is the partial pressure. As the partial pressure is less, the solubility of oxygen at the altitude is less. That is, here I'm going to write solubility of oxygen in the blood, solubility of oxygen in the blood is low at high altitude. The reason is there is a low partial pressure, because we know that from the Henry's law the solubility of gas is directly proportional to partial pressure. Here partial pressure is low and therefore solubility of oxygen in the blood is also low. As a result of this, the people living or working at the high altitude or at the mountains or mountain climbers often found that they feel weak or they are unable to think properly or unable to think clearly. And this kind of symptoms is known as anoxia. The absence of oxygen. This happens due to the absence of oxygen. So all over the result is at the high altitude the partial pressure is low, and because of that the solubility of oxygen in the blood is low. And when the oxygen is low in the body, the person unable to think properly or feel a weakness, a lack of energy in the body. And that is all due to the less in the partial pressure, students. This is one example or one application from the Henry's law. Here, this is the second application of Henry's law. Listen here. He's a scuba diver. Okay. And he is under the water. This is a water level. He is under the water. And above this is another classic example of the Henry's law. See here, this is the water layer, and below that there is a person. And there is high partial pressure, or you can say that generally the pressure under the water is high. The pressure is high. So it means that if the partial pressure of particularly that oxygen is high, all gases have here high partial pressures, and that oxygen is also having a high partial pressure. Along with that, the partial pressure of nitrogen is also high. And from the Henry's law, we know that the partial pressure of any of the gas above the solvent or the solution is equal to Kh into concentration. So it means that this concentration means the solubility. So therefore, the oxygen and the nitrogens are more soluble under the water because there is a high pressure is there. Now listen what happens. When a person inhale the oxygen, along with the oxygen, he inhaling nitrogen. Compared to these two, in the blood, both are soluble. Oxygen along with the nitrogen. But at the normal atmospheric pressure, only the oxygen is soluble in a blood. And here, at the high pressure, the nitrogen is also soluble in a blood. Okay. Now in the blood, there is oxygen and nitrogen both are present. Okay. So this creates the blockage of capillaries due to the presence of the nitrogen. This happens only when a deep sea diver comes towards the surface. Suddenly, when he comes towards the surface, the pressure decreases rapidly, and dissolved gases like nitrogen and oxygen gases are released and forming a bubbles of nitrogen in the blood veins or the capillaries. Okay, and because of that reason, there is a formation of a painful and quite dangerous situation, and that situation is known as Bendt's disease. Bendt's disease. Bendt's disease. And this happens due to the presence of high pressure in the water. At the high pressure, both oxygen and nitrogens are soluble in blood. But when the person comes to the surface, there is sudden decrease in the pressure. So along with the oxygen, nitrogen evaporates, or you can say that diffuses out from the blood, in the capillaries itself. Okay, to avoid this bent disease, scuba divers nowadays using the cylinders, and in that cylinder it contains 11.7% of helium and so 56.2% of nitrogen, and along with that is 32.1% of oxygen. So this is known as an oxygen cylinder. In the oxygen cylinder, there is no only oxygen present. Along with that, there is a helium, and along with the nitrogen is also present. But due to the presence of the helium, the solubility of nitrogen decreases in the blood. Okay, and this avoids the bent disease. The third application of Henry's law is that is soda waters, or you can say that soft drinks. Soft drinks. Okay, in the soft drinks, they add water plus carbon dioxide and some sweetening agents or tasting agents. Okay, but carbon dioxide is soluble in a water. Okay, for example, if there is any container and in that container there is a water is present, H2O, you can make carbon dioxide to soluble in the water only at the high pressure. High pressure. Okay, it means that the carbon dioxide is soluble in water only at the high pressure. Therefore, you can see that when you open the tap of the soft drinks like Coca-Cola, Thumbs Up, there is a bubbles are created, and that bubbles are nothing but a carbon dioxide molecules. Okay, so therefore the solubility of carbon dioxide in the water is done only at the high pressure. Okay, student, this is all about the application of the Henry's law. Let's see the vapor pressure of liquid solutions. Here, the vapor pressure of the liquid solutions. This is very important concept, and for that I use a container and in this container I am going to fill the water. The water molecules are here, or any liquid molecules, not only water, you can take any liquid molecule. Now these liquid molecules gain the energy from the surrounding. When they gain energy from the surrounding, they start moving randomly, and if they gain a sufficient amount of energy, then they start escaping the surface of the liquid and comes out. As they come out, they start colliding with the other gas molecules which is present in the atmosphere, and they lose the energy, and they again come back to the solvent. Again they gain energy and move back to the atmosphere, and they remains there only. And these gas molecules constantly dissolving in the solvent and evaporating. Now assume that these gas molecules are colliding with themselves and also colliding with the wall of the container. Assume that this wall is packed and gas molecules are moving and colliding with the wall of the container, and they are exerting a pressure. Exerting pressure. This pressure is due to this liquid vaporizes and converts into gases, or you can say that this is nothing but a vapor only. This is a vapor, and these vapor molecules are colliding with themselves and also with the wall of the container, and that produces here pressure. Okay, and therefore the pressure exerted by, this is the definition for the vapor pressure of the liquid solution here, the pressure exerted by the vapors, exerted by the vapors above the liquid, above the liquid. Here you can see that these vapors are exerting a pressure above the liquid surface, and there is an equilibrium. Okay, there is an equilibrium because as I mentioned here, some gas molecules get into that liquid, and some gas that liquid molecules get evaporate again. So there is a dynamic equilibrium is established here. Okay, therefore surface in equilibrium with the liquid, So hope you understood that what is the vapor pressure of liquid solution. So only thing is here, we have taken the liquid और इस लिक्विड से कुछ मॉलिक्यूल्स एवापोरेट होके गैस बनेंगे और ये जो गैस मॉलिक्यूल रहेंगे ये कोलाइड करेंगे वॉल ऑफ कंटेनर के साथ या फिर सरफेस के साथ, तब एग्जर्ट करेंगे कुछ प्रेशर को. उस प्रेशर को हम क्या कहेंगे यहाँ पे, वेपर प्रेशर ऑफ लिक्विड सोल्यूशन. ओके, यहाँ पे हम दो तरह के पॉइंट्स डिपेंडेंसी देख सकते हैं. एक तो रहेगा यहाँ पे दैट इज अबाउट द नेचर ऑफ द लिक्विड, द नेचर ऑफ द लिक्विड. ओके, एंड दूसरा जो पॉइंट रहेगा दैट इज द टेम्परेचर. Okay, we'll see one by one now. In the nature of the liquid, we have to think about the intermolecular force of attraction. Intermolecular force of attraction. See here what we have. Assume that this is a container, and in this container I am going to take some liquid molecules. These are the liquid molecules. In between the liquid molecules, there is a force of attraction. These are the force of attractions exist between the molecules. Now what happens? The vaporization is dependent upon the force of attraction, and that itself is known as a intermolecular forces. We can make two possibilities here. The one possibility is weak force, another one is strong force. If the molecules connected with each other by weak forces, then they can be vaporized easily. That is easy vaporization, because it is easy to break a weaker forces as compared to strong forces. In the case of strong forces, it is difficult to vaporization. It means that if any liquid in between that there is a weak intermolecular force of attraction exists, then it escapes very easily and get converts into gas or in the form of vapor. And if it is present in the vapor, means number of molecules, here I can write number of vapor molecules are more. And now we can make a statement here. If there is a greater number of vapor molecules, greater will be pressure. Hence, greater the pressure. So finally we can conclude here that each liquid has characteristic vapor pressure, because each liquid has characteristic intermolecular forces. Okay, so कोई भी अगर एक लिक्विड ले लो उसका एक पर्टिकुलर वेपर प्रेशर रहेगा, क्योंकि हर एक लिक्विड में एक पर्टिकुलर अमाउंट ऑफ इंटरमोलिकुलर फोर्स एग्जिस्ट करता है, विच डिपेंड्स, जो वेपराइजेशन का जो प्रॉपर्टी है दैट डिपेंड्स अपॉन द नेचर ऑफ इंटरमोलिकुलर फोर्सेस. ओके, बिकॉज ऑफ द लिक्विड विच हैव द वीक force of attraction or intermolecular force of attractions tend to escape very easily into the vapor phase, and therefore they have high number of vapor molecules, and that leads to the greater vapor pressure. Okay, we take one example. If you take the ethanol in the container, and in another container you have to take water, H2O, you will find that the ethanol molecules exist more in the vapor phase as compared to water molecules. It strictly indicates that in the ethanol, the intermolecular force of attractions are weak, but in the water, intermolecular forces are strong. Therefore, in the water, vaporization is less and less vapor pressure. less vapor pressure. Whereas in the ethanol, the intermolecular forces are weak, hence easy vaporization, greater number of vapor molecules exert a greater pressure, and therefore here the higher vapor pressure is there. High vapor pressure. Okay students, this is all about the nature of the liquid. Let's see the temperature. When we take a certain container and this container is filled with the water. Okay, now these water molecules have a strong intermolecular force of attraction between them. Or you can say that any water molecules or any liquid, you can say that. So these molecules are interconnected, and when you start heating it, you will find that these gas molecules gain kinetic energy. As they gain kinetic energy, they start moving randomly in all possible directions. And then with the help of the kinetic energy, they break down the force of attraction and escapes out, and creating the vapor above the liquid surface. As much you heat, the greater number of gas molecules or liquids are converted into vapor phase. And this leads to the very interesting fact here, that as you increase the temperature, there is increase in the vapor pressure, because as you increase the temperature, the vaporization increases. Why vaporization increases? Because when you heat any of the liquid, they gain kinetic energy, and due to that kinetic energy, they escape the solvent or the solution. Hence, there is a greater vaporization. If there is a greater vaporization, greater number of vapors are present above the liquid surface that exert a greater vapor pressure. Okay, this is all about the effect of temperature on the vapor pressure and how it is related with the temperature, students. So, hope you understood this. For the next discussion, I will take the vapor pressure of liquid solutions. We'll discuss that in the next video. Thank you for the watching.